Okay. Are we on?
Not yet. Yeah, we are live.
Okay, perfect. So good afternoon, everybody. We proceed with our cycle of colloquium. This week we have again Eric Miller. He came here a year ago. He presented here. He came here virtually a year ago to talk about the satellite CRISM that we launched in the near future. And today he's going to be talking about another one, which is a pretty interesting and new project that MIT is heavily involved, which is satellite ALMA, which is basically a super Chandra, high-resolution, spatially resolved spectroscopy, and so on. For those who don't know, Eric, he finished his PhD in the University of Michigan in 2003. He was a postdoc associate in the MIT for a while. In 2009, he became a research scientist and is there until currently. He works in many different aspects of diffuse gas and galaxies and clusters, groups, and galaxy formation, and a lot on data reduction, processing of software, and calibration of satellites has been, I think, probably the highest activity currently. He was a science working group. He was I'm not sure exactly what the position Eric they had in the CRISM. You were science working group coordinator, right? And
actually, I'm coordinating the in-flight calibration plan. That's what I'm coordinating. But I'm also a member of the science working group as well. Okay,
and currently similar duty with the CRISM satellite. And now also with the ALMA, which is going to be talking to us today. The mission should be launched in the future, not so near,
not so soon.
But it's interesting for everybody. There are many applications. So I give the word to Eric then.
All right, great. I will share my screen, and I assume everybody can see this and hear me, but let me know if not.
Right. Yes.
Yes, you can.
And I just have to move some Zoom windows because they keep showing up in the wrong place. Okay, great. Yeah, thanks very much for the introduction. And it's my pleasure to be here, at least virtually today, to talk to you about ALMA, which is the Advanced X-ray Imaging Satellite. And of course, this is on behalf of the entire ALMA team, of which Renato is a member, along with about 100 other people at this point. Great. Okay, so before I actually tell you what ALMA is and what it can do, I want to put it in a little bit of context. And the context really arises from the recent decadal survey in the United States called Astro2020. And this decadal survey, which basically was going on for the last 2 years and was finally released earlier this year in January, identified 3 main pillars of astrophysics research that should happen within the next 10 years. And they fall into these 3 pillars here. The first is worlds and suns in context. This is especially exoplanets and stellar environments. New messengers and new physics, which really is kind of a new realm of astrophysics where we deal with multi-messenger and transient sources. And then cosmic ecosystems, where we try to understand the evolution of galaxies and other structures throughout the age of the universe. As part of this decadal survey, the survey laid out the missions and the ground-based observatories that they thought would really address these topics. And in particular, one of the facilities that they strongly suggested is in the next decade is something larger than the NASA Explorer scale, but a mission either doing far infrared astrophysics or an X-ray mission designed especially to complement ESA's ATHENA mission. And so this table over here shows the sort of timeline for these various facilities that the decadal survey laid out. And in fact, ALMA, as I will describe it, falls really neatly into this. ALMA would, if successful, would launch in early 2030 and provide this X-ray probe facility. So NASA rapidly implemented this recommendation. Of course, this was the decadal is just a recommendation to NASA, but NASA generally adopts what the decadal says, because the decadal is made up of astronomers and astrophysicists who know where the science should go. And NASA announced an intent to call for proposals for what they call probe missions. And these missions the final selection will be made in sometime in 2025. The proposal itself will likely be due sort of mid or late next year to fly in about 2032 for a total cost of $1 billion US. And ACCESS, as I mentioned, really does provide science that addresses all three of these major topics outlined by the Decadal Survey, which I will show in the next several slides dealing with the science. Okay, but what is ACCESS? ACCESS, in fact, did not just come out of the Decadal Survey, but ACCESS was conceived several years before the Decadal Survey as sort of a probe concept, which was in response to ideas for where the science should go in the next decade. ACCESS is a next-generation X-ray observatory specifically for high-resolution imaging spectroscopy. So I mentioned the mission concept was developed and written up in a report in 2019. This is an engineering conception of what ACCESS looks like, and I'll get into a lot more detail about that later. The real key here are two things at the top of this table, which lists the current ACCESS requirements. The first is the point spread function, or the angular resolution. ACCESS will have 1 arcsecond on-axis resolution and 2 arcseconds at the edge of the field of view, up to 15 minutes off-axis. And as Renato mentioned, you can think of this sort of as a super Chandra or a successor to Chandra. And the key here is that the spatial resolution is very similar to Chandra on axis, as can be seen in this plot down here. Chandra is this black curve. So this is off-axis angle. The y-coordinate here is the point spread function in arcseconds. Chandra actually has sub-arcsecond resolution in the center. However, the mirror design is such that the resolution degrades quite rapidly as you go off-center and gets out to 8 arcseconds when you're about 8 arc minutes off axis. Whereas the ACCESS concept will have a nearly 1 arcsecond resolution across the entire field of view. And this is a major improvement over the already really good capabilities of Chandra. In addition, the effective area, this is basically the collecting area, is an order of magnitude larger than Chandra. The field of view is a little bit larger. The bandpass goes from soft X-rays to sort of medium hard X-rays, similar to what Chandra does. I will point out that another key improvement over Chandra is the slew rate. And in fact, in addition to being a successor to Chandra, you can also think of it as a successor to SWIFT, because this combination of slew rate and the fact that it's in low Earth orbit, where it can respond very quickly to targets of opportunity and transient alerts, mean that it will be able to follow things up very quickly. And that's part of the science goal of this mission. Okay, so in order to get this done, obviously it has to, the technology has to be leaps and bounds beyond Chandra. And so over the last decade or so, there have been developments in lightweight X-ray optics that are now making this possible, along with developments in detector technology that make it possible. And I will talk about those at the end of the talk. Okay, but first, just to see a little bit about ACCESS's capabilities at a glance. I apologize, this came out a little blurry. This blue box shows the field of view of the Chandra ACES-I instrument, which is about 17 arc minutes across. ACCESS, at least the baseline, will have a 24 arc minute field of view, so significantly larger. Really, the PSF is across that field of view is what's important. It will be similar to Chandra's in the center. This just shows you the size of the PSF. But in the outer parts of the field of view, which is again larger, ACCESS will really be much higher resolution than Chandra, and this is a key. The other key is the effective area, or the collecting area. This is shown as a function of energy here. So the blue shows what Chandra ACES-S was at Chandra's launch. It actually has degraded quite a bit in the 20 years that Chandra has been up, and the black shows what it is now. ACCESS is shown in red, and it will be about an order of magnitude larger than Chandra's, basically at all energies. And I have actually lost my pointer. I think my trackpad just ran out of batteries, but let me try restarting it. And if that doesn't work, then I'll just have to point verbally at things. Okay, yeah, they ran out of batteries. Okay, so the lower right plot shows the a couple of other metrics that really show you the capabilities of AXIS. So on the y-axis there, again, is just the spatial resolution, or the PSF, and the x-axis is this thing called the grasp, which is just the product of the collecting area with the field of view. And so it's another, you can think of it sort of as the survey efficiency. The larger this number, the better the mission is at doing surveys. And AXIS is in the upper right of this, meaning that it's just a really powerful survey machine, also with high spatial resolution, which means that the flux limit is very low, and the confusion limit is also very low. And you can see it's no existing mission has the capabilities that it does, and it even outperforms ATHENA, at least in terms of the spatial resolution. Okay. So AXIS, as I mentioned, has a pretty sizable team now of probably more than 100 scientists from around the world. The AXIS was really conceived, or at least the concept was made possible by Richard Mushatsky from the University of Maryland, who spearheaded the initial formulation of the concept, starting in about 2017. The PI for this proposal has been switched to Chris Reynolds, with Aaron Kara here at MIT as the deputy PI. And then the optics are being led by Will Zhang from Goddard Space Flight Center, and he's really been the driving force at developing these lightweight optics over the last decade. And I am the detector lead for this. Okay, and of course, as I mentioned, it's, like I said, it's a large team, so lots of people are contributing to formulating the proposal for this mission. All right, so of course, I want to talk a little bit about the science of AXIS now that you have the context of the Decadal Survey, and what science we really need to be able to address to fit in with the priorities for the next decade. So I think one of the most important things that the Decadal pointed out is that we are entering a golden age of time domain astronomy. You know, it's especially expanding astronomy observations outside of the electromagnetic band and being able to detect gravitational waves for the first time very recently, along with neutrinos, really opens a new window into astrophysics and different topics in astrophysics. So what this plot is showing is, as a function of time, when different missions and ground-based facilities come online and their expected lifetime. And so you can see this is then sorted by waveband. You can see in the blue, these are all of the current X-ray missions and the X-ray missions that will fly soon. And one thing you should notice is that a lot of these missions, such as SWIFT and XMM and Chandra, have been around for more than 15 years, and they're getting a little aged, and they certainly will not last forever. And there's nothing really on the horizon until you hit ATHENA to fill in this time domain, or this desert, if you will, in time domain capabilities of X-ray instrumentation. At the same time, there are lots of facilities in other wavebands, such as the SKA and the Roman Space Telescope, and especially things like the Vera Rubin LSST Observatory, which will be coming on in the next decade. And those will be returning lots of transient events, lots of things to follow up that we just will not be able to do with the current instrumentation that we have in the X-ray band, especially if missions end up reaching the end of their life before then. So AXIS really fills this niche quite well, and this is one of its strong science components. Just to give you an example of what AXIS can do with transient events, here is a chart showing sort of the zoo of those kinds of phenomena. The x-axis here, and actually, I'm going to see if I can change the batteries in my trackpad. We'll just give me a minute, because I really would like to point things out. Let's see if I have fresh batteries. I don't think I do. All right, but while I'll do that, oh, it just connected itself. Hold on a second. I still don't see it, so let me do this. All right, bear with me 1 second, please. This is not something that you imagine happens. All right, there we go. Perfect. Okay, so let me go back into full screen. And let me share that. And I assume that you can all still hear me. Okay. Great. All right, good. Okay, apologies again for that. Okay, so this chart is showing the zoo of transient phenomena, as I said, and the x-axis here is the time scale on which they vary. So sort of from seconds on the left to years on the right. And then the y-axis is just the X-ray luminosity. But in fact, you can convert that into how far back or how far away in the universe AXIS can detect these things and can detect the variability in these phenomena. So, you know, you have the closest stuff, which are things like nearby flaring stars and dwarf nova, which of course AXIS can see just in our sort of solar neighborhood in our own galaxy, up to variable X-ray binaries and nova, and the neutron star coalescence event that produces gravitational wave event. AXIS will be able to detect things like that out to hundreds of megaparsecs. Then up to ULXs and AGN and all the way to tidal disruption events and GRB afterglows, which AXIS will be able to detect basically out as far as we expect them to be, out to a redshift of 10 or beyond. And so AXIS will really enable some really exquisite studies of all of these sorts of events, and some of them covering a very large fraction of the size of the universe. So in order to be able to do this, we need to be able to respond to these events when they happen. And some of these events are very short duration, or we need to get on them fast in order to really understand, really study them in detail. And so the mission drivers for this, of course, I mentioned the fast slew. AXIS will slew something like 120 degrees a minute. We also need high efficiency and fast readout so that we can trace variability going down to very short timescales and get enough photons at those timescales so we can understand that there's really short periods of variability. So one way to think about this is to compare, for example, the Vera Rubin telescope, which is 60 times more sensitive than its predecessor, the Zwicky Transient Factory. AXIS is comparable to this if you compare it to SWIFT. So that's why AXIS is not simply a successor to Chandra, but you can think of it also as a successor to SWIFT, and the sorts of things that SWIFT has done to expand our understanding of the transient and variable X-ray universe. AXIS will do along in coordination with these other facilities at other wavebands. So this is really very exciting. Okay, in addition to just transient sources, of course, AXIS will look far back in the universe at things that are just starting to form. And so one of the things that we really want to understand are what the first seeds of supermassive black holes were, and how did they go about growing into the supermassive black holes that we see at the centers of every galaxy today in the local universe. So over here on the left, this is showing some models of black hole growth. That's what's plotted on the y-axis here as a function of redshift. And the different colored models here are just for different sorts of seeding. The light colored ones are for light supermassive black hole seeds. The dark ones are for heavy seeds. Our current observations basically extend only to redshift of 6, only redshift 6. But you can see the models don't really diverge at those distances. It's beyond redshift 6 where you start to see differences in the models that will tell you, help to tell you exactly how these things have been seeded and how they have grown. AXIS will allow us to push beyond that redshift and enter this domain. Over on the right is a plot of the survey flux limit as a function of survey area for several previous surveys and a couple of future ones as well. And so in order to do these kinds of surveys, right, you want to be down here in the lower right with the largest area and the lowest flux limit. These gray shaded regions show you how many AGN at redshifts greater than 6 you expect to see in the survey. So for instance, up beyond this point, you expect 1,000, 100, et cetera. And so these 3 red points show 3 notional axis surveys to address this. And you can see that all of these surveys are going quite deep to the point where we're getting dozens of AGN at redshifts greater than 6, which is an order of magnitude better than previous surveys have been able to do. Comparable to ATHENA in some respects, but significantly better for the medium and the deeper surveys as well, simply due to the high spatial resolution of AXIS compared to ATHENA. Okay. This is a simulation of one of these deep fields. This is a 5 megasecond exposure with AXIS, and now this is the entire 24 arc a minute field of view. And so all of the white dots you see in here are AGN. There are about 3,500 of them. All of the red things you see are galaxies. There are about 5,400 of them. So even just this is a very deep exposure, but this one pointing will return just an abundance of information on these objects. And again, just to stress the difference with Chandra, of course, Chandra did a couple of deep fields, including the Chandra Deep Field South, which was 4 megaseconds. However, AXIS will have very similar point spread function and therefore very similar confusion limit and flux limit at the center as it has at the outside. So if you compare these two regions in AXIS, there's actually very little difference in the point spread function between those. Whereas Chandra, that far off AXIS, the point spread function greatly increases the confusion limit and the flux limit you're able to reach. So AXIS, the takeaway here is that AXIS really is a survey machine. Okay. Likewise, AXIS can push down X-ray luminosity functions of those same AGN. So these are luminosity functions for AGN at redshifts of 6 to 7 and redshifts of 7 to 8. The blue is just the sort of the expected model. The red here are what the ATHENA WFI will be able to do with a 5 arcsecond PSF. AXIS will go an order of magnitude deeper than that. At 6 to 7, redshift of 6 to 7, a redshift of 7 to 8, it's about a half an order of magnitude, but we're getting to the range where we can start to discriminate different theoretical models of AGN evolution that tell us what this luminosity function will look like at these very distant redshifts. Okay, a little closer to home, AXIS will, of course, be able to observe anything that's intervening between us and these very distant AGN, which are an interesting science topic. So, for example, AXIS will observe lots of galaxy clusters and lots of galaxies as well. And the fundamental science that we want to address here is to understand how feedback processes affect the formation of and the evolution of these structures. So, for example, we know that AGN feedback plays a very important role in shaping galaxy clusters, even at large distances, certainly compared to the size of the supermassive black hole that is being fed as part of the AGN. So it will answer questions or address questions such as how is the AGN fueled, and then really difficult questions that I don't think we have an answer to, including how does the AGN actually distribute that heat over the much larger intercluster medium to prevent things like runaway cooling. And then, also importantly, how do these processes change over time to produce the structure that we see today? And likewise, in smaller systems, such as galaxies, where stellar feedback also plays a very important role, AXIS will help to tell us what the relative role between AGN and stellar feedback is in shaping the galaxy. And a really open question now for galaxies is, does the circumgalactic medium have a cooling flow problem in the same way that galaxy clusters used to have a cooling flow problem? This is something that's just really not well understood, simply because we don't have the X-ray instrumentation able to address it. And again, seeing how these sorts of feedback processes change over cosmic time is important to understand how they affect the formation of galaxies and the structures that we see today. So just to give you a couple of specific examples here, these are two galaxies. The top panels here show our ideas of the impact of stellar feedback on the structure of the galaxy. So this is NGC 3079. This is an optical and H alpha image, and you can clearly see the super bubble popping out of the center of the galaxy of ionized gas. With Chandra, you can see that it also shows up in X-rays, meaning it's very hot, millions of degrees. But the Chandra observation, which is fairly deep, is really only is still counts limited. It's only able to scratch the very surface of this. With AXIS, we'll be able to go much fainter and really start to trace the structures here and get down to the background limited regime as well. And we'll be able to do this for galaxies that are out to distances of 50 milliparsecs. We'll be able to resolve the wind structure, this sorts of structures. Whereas at all redshifts, we'll be able to see the galaxies. We'll be able to resolve things at galactic scales and still learn quite a bit for galaxies across cosmic time. The bottom panels show the impact of AGNs on galaxies. This is NGC 3393. Again, this is an H alpha image where you see all of this ionized gas being heated by the AGN. In Chandra, again, you see evidence of the same sort of extended structure, but there are no details, and this is clearly counts limited in the 500 kilosecond observation. In a 200 kilosecond simulated observation with AXIS, that's the AGN is shown in green. The hot gas traced by iron 18 is shown in blue, and you clearly can differentiate the two of these and start to understand what this structure looks like in detail. And a lot of this is the effective area of AXIS that's helping us do it, but a lot also is the low background because we're in low Earth orbit. And that will really help us to push towards low surface brightness emission, both in these kinds of galaxies and in other regimes as well. And in fact, in one of the regimes that's closest to my heart, that low background will help us to probe the most tenuous hot structures in the nearby universe. And this is the warm hot intergalactic medium, which still remains somewhat elusive. So this is a simulation showing the X-ray brightness of the plasma in the WIM. And at the nodes of this warm hot intergalactic medium, this is where you find collapsed structures such as galaxy clusters. And so, for example, here's a galaxy cluster right here. This circle shows the limits of what Chandra can do. And this is Chandra in a couple million seconds worth of observations in order to map out this large region. AXIS will be able to detect emission out to several times further than Chandra. Chandra has gone out basically to R200, which is close to the virial radius of the cluster. AXIS will be able to map emission out to several times the virial radius of the cluster. The key here, though, is the speed at which AXIS can do that. And part of that is the combination of effective area, but also field of view. The field of view as AXIS is large enough for a redshift 0.1 or further system to cover in a single shot out to twice the virial radius. And this is really great because, first of all, you spend less time mapping a cluster, but also it allows a simultaneous background measurement. And that's key because in these very low surface brightness observations, it's generally the systematic uncertainty in the level of the background that drives the limit to which you can measure this very faint emission. And that systematic uncertainty is driven by time variable things largely, such as solar wind charge exchange, or even just the variability of the galactic cosmic ray flux, which is mediated by solar activity. And so getting these contemporaneous backgrounds really will help us to be able to measure this very faint stuff. In addition, just having a low particle background because of the low Earth orbit, where a lot of the particles are shielded by the Earth's magnetic field. Both of those are key to being able to measure this very low surface brightness stuff. Okay, so that's really a whirlwind tour of the science. There's actually lots of science, as you might imagine, that you can do with a facility like this. And I will talk a little bit about at the end about how you can learn more about that science. And you probably are coming up with your own ideas as well about things that you can do with AXIS. But I want to spend the last part of this talk just talking about how we can do it, because it's great to talk about the things we want to do. It's very important to show that we actually can do it. Okay. So AXIS really is a simple design. I put simple in quotation marks here because, of course, it is still technically challenging. But the design itself, the idea was to make it as simple as possible. And it's simple in that you have a telescope up here, which focuses X-rays. And 10 meters away, 9.5 meters actually, you have a focal plane with a single X-ray imaging instrument on it. And that's all there is. There are very few moving parts in it. And the idea is to make it simple and robust so that it works and works for a long time. Okay, so however, each of these components, the telescope and the focal plane, do require technology that is leaps and bounds over what has flown before. So I'm going to talk about both of those things. But before I do, I realize some of you might not be familiar with how X-ray telescopes work, because they're not the same as optical telescopes. The key difference here is that an optical telescope, you can basically take a parabola of glass and illuminize it, and you have a telescope. And that's something that humans have been doing for 400 years or so. And obviously it's much better now than it was hundreds of years ago, but it's still fairly straightforward to do. The problem is that X-rays, unlike optical photons, do not reflect in normal incidence. They are just absorbed by this, and so you cannot focus them using a telescope like this. So this animation is essentially showing that. Instead, what you generally do for all of the modern X-ray telescopes that have been built is you use this technique called grazing incidence, and you turn the mirror on its side so that the photons, the X-rays, arrive at just a couple of degrees from parallel, and they reflect off a primary and secondary mirror shell, and then are focused down on the focal plane where they can be imaged. Okay, so this works very well, and in fact, Chandra has demonstrated that you can get 1 arcsecond resolution doing this. A couple things you probably noticed, though, compared to that original just flat, or the original normal incidence parabola that I showed, the effective area here, the collecting area, is tiny. This only has 4 primary reflectors on it, and so if you turn this on its side, and I'll start this movie over again. If you look at the front of the mirror, there's actually very little area that is actively collecting photons. So that's an issue. For that limited amount of area, you also have an enormous amount of material, because you have to turn that mirror on its side. So compare the amount of material here to the amount of material in that very simple parabolic reflector. And so it turns out that X-ray optics of this sort have a very high cost to collecting area ratio, as opposed to things like optical telescopes. And in fact, for Chandra, this video was made for Chandra. The Chandra X-ray Observatory has optics like that, where they only have 4 shells, exactly like this. And so the effective area of Chandra is limited in order to get this really exquisite point spread function down at the focal plane. Having said that, however, the mirrors are heavy. They were very expensive. They're made of glass. And when you launch things into space, mass equals money. So the idea is to produce lightweight optics where you can much more efficiently fill this opening with reflective optics and maximize your throughput. That's why X-ray astronomers generally talk about effective area, because the diameter of the telescope doesn't mean anything if you don't know how much of that diameter is actually filled with reflection, filled with optics that can focus the X-rays. So that's why we talk about effective area. Okay, so the breakthrough that has been accomplished over the last decade or so has been engineered by Will Zhang and his group at Goddard Space Flight Center. And their plan basically is to use a hierarchical method to assemble a lightweight and very efficiently filled X-ray telescope aperture. And the key to this is using this material called monocrystalline silicon, which I will talk about a little bit about exactly what that is. But the point is that it's inexpensive, and it's readily available, and it's easy to scale. And so the way this works is you start with these mirror segments. These are made of monocrystalline silicon and shaped like this. Each one is, I think, about the size of a playing card. And you use these as your primary and secondary mirrors. And then you assemble these segments into modules. A module is shown here, where you just kind of stack them on top of each other. And so this part of the module, this stack, becomes the primary mirrors. This stack becomes the secondary mirrors. And so X-rays come in like this. They go in through these little slots between the modules, and they reflect off of one primary, then they reflect off the secondary, and then they're focused. And so once you have one of these modules, then it's fairly straightforward. It's just kind of assembling this all into a telescope. You stick the module into this shell, which is called a metashell. And then you take this metashell and you put several metashells together, in this case, 6 metashells, to make the full mirror assembly. And so if you compare this to what you saw in that video, the opening area is much more efficiently covered by reflective surfaces, as opposed to what you saw in the Chandra design. Okay. And this turns out to be a lot more lightweight. If you were to try to do this with glass, first of all, it would be very difficult to assemble because somehow you have to attach all the things, but it would also be really, really heavy. Okay, and that's why the idea is to use this monocrystalline silicon, because it's lightweight, it's readily available. And so this is how you go from a silicon block into one of these mirror segments. The nice thing about this is that the silicon blocks, as I mentioned, are readily available. They're not very expensive. It's the same sort of material that the semiconductor industry uses, which is why there's a large supply of it that's not super expensive. And so you start with the silicon block, you shape it a little bit, and you you basically slice off a mirror segment, and then you do some polishing and some post-processing to that. And then you take the rest of this block and you go back in the process and you just keep slicing mirror segments off of it. And so you can imagine that this is a really sort of like a assembly line procedure. This is something you can do in a factory and just churn out mirror segments in a massive and parallel scheme. And that's good because access to fill the mirror, I showed in the last slide, needs 18,000 of these mirror segments in order to populate this entire thing. So I'm not saying it's easy, but it is something that you can do on a large scale for a mission like AXIS. And in this way, it's much more of a, or much less of a sort of artisanal telescope design or telescope fabrication, which you could argue was true for Chandra, and much more of a factory and efficient fabrication technique. Okay, and then so once you have this nice mirror segment, you polish one side of it, which will be the reflective surface. The backside is not reflective. You make sure it's not reflective because you don't want things bouncing off the backside. And then there are these little bond pads, and this is how you stack one segment on top of each other by using these bond pads. All right. And so, you know, I would say that the most challenging thing here is not necessarily creating these segments, because as I said, once you know how to do that, you can do that en masse. But it is aligning all of these things to make sure that the focal point of all of these modules is the same, so that all of your photons for coming from the same point in space end up in the same point in the focal plane. All right, and so Will and his team have demonstrated that they're on the track to making this possible. So for example, up here, this is a single pair of primary and secondary segments, and they demonstrated just about a year ago that this single pair meets the image quality that we need, less than 1 arcsecond PSF. And so what they're working on now is basically stacking up multiple segments of primary and secondary pairs into a multiple segment module. And last year, they demonstrated that they could do that with 5 segments stacked. They could reach 3 arcseconds half power diameter. And so this is on the track, assuming that the technology develops the same way the single pair modules did. We're on a track to get to the requirement by the time the proposal has to be submitted late next year. So this is pretty exciting. Definitely watch out for more information on this as the technology improves. Okay, so that's the telescope. At the other end of this 9.5 meter focal length is the focal plane. And the keys to the focal plane are that in concept, it's not very different to what has flown on Chandra. But in practice, it does need to be much more capable than what flew on Chandra. And in particular, it needs to be very fast readout. And I'll explain why that is in a second. So right now we're baselining 2 detector technologies for AXIS. One is based on Ccds. These are actually direct descendants of the CCD detectors that flew on Chandra and Suzaku. We call them digital CCDs. And these are fabricated by MIT Lincoln Lab and then tested in my lab here at the MIT Kavli Institute. The other technology that we're considering are Cmos devices. In this case, they're called hybrid Cmos devices, and these are under development by Penn State University. And they both have pros and cons, which is why we're considering both of them. And I'll get into those in a minute. This is the concept that we had in that initial concept study report back in 2019, which probably will change in the final version. But before I get into the pros and cons of each of those, I want to talk a little bit about why they need to be different from a Chandra. In order to do that, similarly to the telescope, there are differences between CCDs that detect X-rays and CCDs that detect optical photons. In fact, they're really the same CCD, but just the way that they're operated is different. So over here, this is going to be a movie that I'm going to show, and this is kind of a slice through CCD, or a charged coupled device, that's detecting optical photons. And so the top here is the entrance window of the CCD. So optical photons come in here, they interact in the silicon substrate of the CCD, and each optical photon that interacts produces one electron by the photoelectric effect. There's an electric field that's applied across the CCD, and that the electron that's produced feels that electric field and drifts in this direction, where then it's captured within one of these pixels and held there until the CCD is read out. Okay, so I will show you the movie. Each of these little red things, this is an electron that's produced by a photon interaction. I don't show the photons coming in, but just imagine they're producing these electrons. The electrons they drift around just by random motion, because there's some thermal motion in there, but they drift in response to that electric field, and they're collected down in these pixels. The key about optical detectors is that you get proportionally one electron per photon. And so you end up counting the number of electrons that accumulate in each pixel, and that gives you an idea of the number of photons. So it's directly related to the flux of the object that you're looking at. But you can integrate for as long as you want, collecting photons or collecting electrons in these pixels, as long as you don't exceed the well capacity, but that's something generally hundreds of thousands of electrons. That's very different from the way that X-ray CCDs are operated. I'll show that over here. In an X-ray CCD, again, you have the same or very similar structure of some silicon substrate divided into pixels. In this case, I've just made the pixel size smaller, which is why there's lots more of them. But the X-ray photon comes in here. In this case, you just have one photon coming in. That one photon produces lots of electrons just because it's very energetic. Hundreds or thousands of electrons are generated in the interaction. And those electrons, again, feel the electric field and drift down to where they're collected in pixels. But unlike with the optical CCD, all of these photons are associated with a single X-ray, all of these electrons are associated with a single X-ray photon. This is good and bad. The good thing about it is that if you sum up the total number of electrons here, which you do when you read this out, then that gives you an indication of the energy of the original X-ray that produced them. So in fact, X-ray CCDs are spectrometers. They are integral field units. You are able to measure the energy of incoming photons without putting a filter in front of it, such as you have to do for a typical optical detector. The drawback, however, is that you need to be able to remove the signal before the next X-ray comes along, because if another X-ray comes along before this charge is read out, it will simply add its signal to this one, and you will not be able to reconstruct the energy of either of those original X-rays. And that's what we call pileup, and that enforces a bright source limit to the instrumentation, and that's a serious problem. We have to read out one X-ray photon, or the signal from one, before another arrives in the same location. Okay, so that's actually driving why these need to be high speed or fast readout detectors, because the effective area has increased so much. We need to be able to read out at a correspondingly faster rate in order to avoid pileup. Likewise, collecting all of that X-ray signal turns out to be challenging. And I'll show a little bit about why that is. So now this is a simulation. Again, this is a slice through a CCD, and what's being plotted here is the strength of the electric field in the vertical direction. So there's always an electric field that's applied, so that when you produce that little cloud of electrons, it will drift very quickly down to this where the pixels are defined and sit there until it's read out. Okay. The detectors that we're designing for AXIS are quite a bit thicker than the CCDs that flew on Chandra. And part of the reason for that is that we want higher quantum efficiency at higher energies. So what I'm plotting over here, this is the absorption probability for photons of 3 different energies. And so the very softest X-rays, basically, they enter the entrance window here. They interact very close to where they enter. They just don't penetrate very far into the silicon, and they produce a cloud of electrons there. That cloud, however, has to travel this entire distance, diffusing and getting bigger all the time before it's collected in these pixels. And so this causes issues for these the very softest photons, because it's easy to lose electrons outside of the island of pixels where most of them end up. And if you do that, then you lose a corresponding amount of the recorded energy of that X-ray, and it's very hard to reconstruct the energy of the original X-ray. Okay, so just a couple more animations of that. So now this is a notional axis device. Again, this is the entrance side of the CCD. This is where the pixels are defined by the various electric fields of the gate structure. So here's a 6 keV photon that comes in, and it doesn't penetrate very far, only 8 microns before it interacts. A photon of that energy produces about 1,600 electrons, and the goal is to collect them all. Okay, so there are the 1,600 electrons being produced and then drifting and being collected in the pixels, and I'm just looping the animation so that you can see it multiple times. I should point out that this is slowed down tremendously. This entire process is less than a nanosecond. This is very, very fast. And so, but what you can see in a device like this, instead of having that charge concentrated in just a couple of pixels, it's spread out over on the order of 16 pixels or so. And so you need to get the signal out of all 16 of those pixels and to reconstruct the energy of the photon. You can also, because this is a 6 keV photon, it can actually penetrate quite a bit deeper. This is a less extreme case, but you see, even in this case, we're still dumping signal into something like 9 pixels. And one thing I didn't mention is that when you read out the CCD to get all of the signal, each time you read a pixel, you introduce a small amount of noise in there from the amplifier. And so you end up introducing noise into each of these pixels. So the more pixels that you read, the more noise that you get, and that noise degrades your spectral resolution. And that's exactly what I say here. You need to charge to summon all these pixels. Each pixel contributes noise. All right. So this is a bit of a complicated plot, but this shows the 3 columns here show different energies of photons, 0.2, 0.5, and 2 keV. And just look at the top for now. So this is showing an example where we have 4 electrons of readout noise, which means every time the readout amplifier reads a pixel, it produces 4 electrons RMS of noise in addition to whatever electrons are there from the actual signal to read. And so this black curve shows the best case scenario. Basically, if you just had one giant pixel, or you didn't have to worry about this pixelation effect, this is your spectral resolution in that case. And you can see as a function of energy, it's not very bad. However, then if you divide these into pixels, for instance, 16 micron pixels, which is what we're baselining for axis, you can see that the addition of the noise in all of the pixels that go into reconstructing this event really degrades your spectral resolution, basically at all energies. And in fact, because we have to enforce a threshold so that we don't end up getting noise events, you start to lose events and your quantum efficiency degrades as well. The bottom plot shows what happens if you're able to reduce the amount of per pixel noise to 1 electron. You can see things get remarkably better. So this is the challenge. Right now, 1 electron's noise basically is not possible with these kinds of devices. No one has demonstrated that with these particular kinds of devices. 4 electrons is pretty easy. The plan is to get somewhere between. Right now, I think the requirement is less than 3 electrons, which is similar to what the noise level that we had on both the Chandra CCDs and the Suzaku CCDs. However, those CCDs were operating, reading out much more slowly, and the noise increases when you read out fast. So this is the challenge for the detectors that we're developing. But it's a challenge that we have. We certainly have a plan to show that it's possible, and it is. Okay, so this is the notional focal plane that we have for axis. We will have 2 detectors on a side, a total of 4 detectors, quite similar to the Chandra ASIS I layout, although each CCD or each detector is larger in format. Pixels of somewhere between 16 to 24 microns. These are sufficient to sample 1 to 2 arcseconds PSF. The field of view somewhere between 2 and 4 times Chandra's solid angle. Again, this is the key, I think, to me, that we need to increase the frame rate over Chandra. So the effective area of axis is about 10 times Chandra. And so just to keep the same pileup limit as Chandra, we'd need a frame rate that's 10 times Chandra ASIS. But really, we'd like to do better than that. We'd like to be able to observe brighter targets than Chandra was able to observe without worrying about pileup. And so the goal is to go to 20 frames per second or even faster, which would be 70 times the frame rate of Chandra. And the key to do that then really is to keep the noise low, because noise degrades the spectral resolution, which is also important. And so the interplay between being able to go fast enough but keeping the noise low is what we're in process of demonstrating right now. And again, these will be twice as thick as the Chandra ACES Ccds, which has its own issues for spectral resolution, but really improves the quantum efficiency of harder X-rays. So right now, the science team is hard at work developing their science requirements, and that's really what needs to drive this development, especially things like if soft spectral resolution turns out to be more important than having a really good bright source limit. Those kinds of things are things that we're considering right now. Okay, so this is the status of the two kinds of detector technology. So the first are these digital CCDs. And as I mentioned, these have direct heritage from CCDs going back 30 years and built by MIT Lincoln Lab and characterized by the group that I'm working in here at MIT. Back to ASCA days, but also Chandra, Suzaku, and XTE as well. The strong case for CCDs is that they have proven performance over these 30 years. And even though we're driving them faster, it really is just another step in the technology development. So our recent demonstration is of a smaller pixel and smaller format device that we're running the readout rate 20 times Chandra. This is not the frame rate, but this is just the rate at which we read out pixels. And in fact, we'll have to have more readout nodes in order to get the frame rate that we want. And that's the next step, is to demonstrate that. We have demonstrated that even running at this very fast rate, we have low power, and that's due to some improvements in how the transfer gate structure is designed. We've also demonstrated that we have met the noise requirements, and that's due to some advances by Lincoln Labs in the particular output amplifier design. We have very good charge transfer efficiency. These devices are radiation tolerant, and we're going to be in a low inclination orbit, actually, where the particle radiation is fairly benign and does not introduce much charge transfer inefficiency, which is the drawback of CCDs. And we have demonstrated that we have the thickness that we require. So right now we're operating a device which is very similar in size to what we need to have on axis and in pixel size, both pixel size and in total package size. In addition, it has multiple outputs, probably a factor of 2 fewer than we need for axis. But by the deadline of this proposal that we're putting in, we will be able to demonstrate that we meet the noise requirements at the frame rate that we need to maximize the science on axis. All right, and then the other technology that we're exploring are these what are called hybrid Cmos detectors. They're actually very similar to CCDs. They're in that it's still just a bulk of depleted silicon with an electric field across it that the photon interacts in. And then that is also collected in pixels in the same way as a CCD. However, it's not read out bucket brigade style across the device as a CCD is, but instead the detector and then the readout array are bump bonded together. So each pixel basically has its own readout. Because of that, CMOS devices are radiation hard. There just is no such thing as CTI. They're also inherently low power because you don't have to constantly have these transfer gates being clocked at several volts. They're also four-side abuttable, and they're inherently high speed. They can fairly easily get up to 20 frames per second and higher. The drawback of them is that they just don't have the flight heritage right now that CCDs do, but that is changing. X-ray, these particular devices or heritage devices of what we would fly on axis flew on a rocket flight very recently, and there is a CubeSat approved for the Penn State group to fly X-ray hybrid CCDs as well. The readout noise is not quite where it needs to be for axis, but again, that's something that's improving. And we're certainly hoping that over the next year, we'll be able to demonstrate that these are feasible to use for axis as well. All right, so the message I want to leave you with really is that axis will be a powerful observatory for high resolution X-ray imaging spectroscopy in the 2030s. And this technology that I spent the last few minutes outlining really makes it possible to do that. It will be complementary to ATHENA in whatever form ATHENA ends up taking. It also addresses a lot of the themes that are important in the recent US Decadal Survey of Astrophysics. So this is the timeline if accepted in late 2025 as proposed. It should launch in early 2032. And then the final thing, if you want to learn more about the Axis science, especially from the experts who actually know a lot more about the Axis science that I summarized here, there are these monthly Axis science seminars. They're on the first Fridays at noon Eastern time, or you can watch them on the Axis YouTube channel. I don't know if there has been one so far, which happened last Friday, but just use this QR code and you can go there and watch that, or you can watch any of the previous Axis presentations that we've given. And now I'm happy to take any questions.
Okay, thanks very much, Eric. So I know that you're tied a little bit with time, so you let us know when.
Okay, I'd probably have 10 minutes.
Okay, perfect. So let's open for questions then. Okay, Roderick.
Hi, Eric. Thank you very much for the nice overview talk.
Sure.
Very nice. Can you explain from the technical or engineering side what is actually involved in this decreasing of the pixel readout noise? You said, for example, for the Cmos, now it's 6.5, and you expect this will go down. So how does this process actually work? What do you do to, right?
Yeah, of decreasing the readout noise. I think on the Cmos, I will preface this with saying that I am not an expert on the Cmos noise. Part of this, I know that at some point there was some crosstalk issues from pixel to pixel, just because the pixels are crammed in so tight together, and you end up having to read out electronics basically right next to each other. So at some point, instead of reading out operating individual pixels, they actually sort of combined them, so they were only using one pixel, and that greatly reduced the noise. The noise in that case was not really random Gaussian noise. It was definitely crosstalk noise, but that was one thing that reduced the noise. I suspect reducing the scale of things of the readout electronics also would help in that. That's a good question for the Cmos devices, and to be honest with you, I don't actually have an answer for how that will be. I can say for the digital CCDs, there are a couple things you can do. So the real advancement went for the CCDs that we have went from changing the output or redesigning the output amplifier. So we had initially the CCDs that are flying on Chandra and that flew on Suzaku use these things called MOSFETs. And these PJ FETs are basically an improvement over that, which enables you to have high responsivity, and that effectively reduces the readout noise by redesigning the amplifier. So some of it is fiddling with the design of the amplifiers. There are other things such as the operating temperature at which you're running is also important. The main thing is the speed. The noise changes drastically with speed. And so if we can think of ways to be able to run each output more slowly, that will alleviate the requirement on the noise of the output. And part of that is just putting in more outputs, for example, or even more CCDs, making the CCD smaller and putting more of them in there.
Thank you. And I had a scientific question. You showed a very interesting figure I had not seen before of the space density of black hole seeds from Ricarte, I think.
Yeah, it's back
Ricarte et al.
Space density is this one, which probably this one.
Yeah, right. The left panel. So here, then, I guess you expect to get the redshifts from somewhere else.
Yeah, this is not the space density. It's actually the
Oh, it's okay.
it's the mass the mass growth rate of the black hole seeds.
Right.
Yep. The redshifts, I think you're right. The redshifts probably do have to come from somewhere else. Again, this is not my science.
Yeah, no, it's fine.
For the AGN, I mean, if they have if they have an iron line, you can get the redshift fairly easily from AXIS itself if you're able to observe the iron line. But otherwise,
yeah, I was wondering if this maybe assumes photometric redshift from LSST with Roman, or maybe
I think it's I suspect that
James Webb.
LSST and Roman are the things that are giving us the redshifts for these. Yeah. And that's why having those concurrent surveys, or even the surveys before AXIS flies, will be very valuable.
Thank you. Good luck.
Thanks.
Okay, more questions? Rebecca?
So, hi, Eric. Thanks
Hello.
for the talk. So I was wondering if there is like any initiative from the team to try to avoid the degradation on the soft X-rays. And that you showed in the very beginning, you're comparing, you're showing the degrading, picture.
Yeah.
So the effective area at launch, right, for Chandra, and you see that it's degraded a lot. And I don't know if there is any technical issue that can be avoided and was learned from Chandra too.
Yeah, I'll say we learned a lot of lessons from Chandra. We've also learned a lot of lessons from Suzaku, which, as you may know, suffered from similar things. And in fact, XMM, to a much lesser degree, fortunately, also suffers from some molecular contamination. So we do have some plans to mitigate this. The key one is keeping everything clean on the ground, of course, and making sure you understand all of the materials that you end up flying. But it's important to have mitigation tools on orbit. And so one of them is the plan to have a warm filter. So the real problem is that if you have any sort of volatile compounds in the environment of the spacecraft, they seek out the coldest surfaces. And in this case, certainly on something like AXIS, the coldest surface will be the CCD, which is operating at somewhere, between -70 and -100 Celsius. And that's the problem with Chandra and Suzaku. That was the coldest surface. So one strategy to mitigate that is to make sure that that surface is not exposed to parts of the spacecraft where you might have these volatile compounds building up. And so one thing you can do is just seal everything up and have a filter, effectively your optical blocking filter, which you need anyway, and keep that at a temperature where where volatiles will not build up on it at temperature, something like room temperature plus 30 degrees, something like that. So that's our plan for this. I will say that that design actually flew on Hitomi, on the CCD of Hitomi. And in fact, even also the microcalorimeter on Hitomi had this series of contamination blocking filters, sort of they're actually also thermal filters, because the microcalorimeter had to operate at such low temperatures. There was no evidence on the CCD that contamination built up. Of course, the mission only lasted a month, so we didn't get very much information. But certainly, I will say on Suzaku, the contamination that we saw on Suzaku would have been noticeable after a month. So that's a good sign that maybe they actually mitigated it. But that's the idea basically, is to prevent that material from getting to the cold parts of the focal plane.
Okay, thanks.
And I agree that that's a very serious concern, because a lot of our science is concentrated in this region, and this is really where we'll, certainly the science I'm interested in is down at these energies, and this is really where we'll learn a lot of interesting stuff.
Yeah, I was actually wondering, like, that, because I don't know, it felt to me that you said the last few phrases that you're trying to see a science driver between the good soft spectral resolution and also the bright source limits, right? So I was wondering, yeah, how it was fitting here. Yeah, cool.
Yep. Yep.
Thanks.
Okay. So Eric, I had a couple of questions. One, you didn't mention the spectral resolution of the instrument at the beginning, but and this would be interesting to know. But you're saying that if you actually can reduce in one of your plots the electron noise to 1 by a factor of 4, you looked in the plot that you could go for something like 100, something like 50 electron volts in spectral resolution. Is that a good assessment for that?
Yeah, 50 is certainly feasible. I will say, yeah, so if we go to 1, I will say 1 electron is very challenging. It'd be fabulous if we could get to a single electron readout noise. It will be challenging. This is effectively the theoretical limit, though. I mean, 1 electron that you're adding to a 200 electron photon really doesn't make this much wider at all. So there's a fundamental limit. There's a theoretical limit just because the number of electrons that are produced by this X-ray interaction is not always the same. There's a distribution. The distribution is not a Poisson distribution. It's actually about 10% narrower in variance than a Poisson distribution. It's called the Fano factor or Fano distribution. But that's a fundamental uncertainty that you can't get beyond because we're using silicon to observe these. But 50 eV is certainly within the realm of possibility. In fact, I believe the Suzaku XIS, at least before flight, was getting close to that at carbon K. Suzaku, of course, was in low Earth orbit, but it was at high inclination, so it went through the South Atlantic anomaly where there's a lot of radiation damage, and that degrades the spectral resolution greatly. So Suzaku didn't keep that resolution very long. One of the reasons we're putting Axis in low Earth orbit is because it's a benign environment, and so we expect that the spectral resolution and the charge transfer inefficiency will not change very much over the life of the mission because of that.
I thought that, well, Axis is also low orbit, right? This
yeah. So Suzaku was too. They're both low Earth orbit, but it's there's the low Earth orbit is a really complicated place. There are places in it that are very benign, and there are parts of it that are really, really horrible. And of course, that changes with time as well, all because of the changing magnetic field of the Earth.
Okay. Well, one of the advantages that should be included in the, let's say, the accuracy perhaps of measurements, the difference between low orbit and high orbit is, the classic example is XMM, right? Those who dealt with XMM know the nightmare that you have to take into account for the non-cosmic background. And this really creates an uncertainty on the accuracy of things that you can actually measure, and the Axis would not suffer that.
That's right. That's right. I mean, I would argue that, well, there's some who argue that ROSAT had the lowest background of any X-ray mission, which I think is probably true, but not far behind it was Suzaku. And the really nice thing about Suzaku is that its background was low, but it was also really repeatable. I mean, the systematic error on the background was very low, and that's the sort of thing that we want for Axis as well. And being low Earth orbit, as I said, there's some parts of low Earth orbit, like the South Atlantic anomaly or going over the poles, where the magnetic field and the radiation belts get very close to the surface of the Earth. And that's just a really terrible environment for this sort of instrumentation. But there are other places where the shielding from the Earth's magnetic field is really, really helpful. And that's where we're trying to put Axis, into that kind of orbit.
Okay, thank you. So any more fast questions? Okay, if not, so Eric, before you go, could you take 1 minute and tell us about the access to data in general, because many people are not familiar yet with the GTO, GO access to, it is really early on the mission, I know.
Yeah, it is, yeah.
General, yeah.
And I'll say that, I mean, yeah, we're talking about 2032, so who knows what the rules will be, but I can certainly give you my opinion as long as you understand that it's my opinion. But I expect that, and I'll put this up in case no one caught the QR. Somebody didn't get the QR code. you know, I expect it will be sort of similar to what we have today. NASA actually hasn't told us or told any of the proposal teams what they're expecting for the lifetime of the primary mission. It could be 2 years, it could be 5 years. I would expect that for $1 billion mission, it's probably on the order of 5 years. They also haven't really told us, you know, if there will be some kind of guaranteed or science working group time, or if this will be from the beginning a facility class mission where there's just a geo program and anybody can apply for it. Given the way that things have been headed lately with NASA, I expect the latter is more likely, and that the idea is that we build this mission with some, you know, specific science goals that we outline, and those science goals are sort of like key projects that the mission will tackle first. But that doesn't necessarily mean that the proposal team or the science working group has sole access to that data to begin with. That data could easily become public right away. And you know, my opinion is that's probably what will happen, that the early data from this even will be public. And then there will be an opportunity for people to apply for time through something like a guest observer program. Yeah. And certainly, you know, I imagine that would certainly be open to people in the US, and it could easily be open to people around the world as well. So I know that NASA is moving towards a model where they want to make sure that the American public is getting something for the tax money that's being spent, and especially for $1 billion mission, that means having basically having all scientists having access to the data from the mission.
Okay. Thank you. So
Sure.
Thanks a lot for the talk. It was very, very interesting.
Great.
And I guess everybody has your information there. If there are any further interest or requests, you can probably just send you an email and talk about it.
All right, great. Well, thanks very much. Thanks everyone for being here and paying attention.
Thank you.
All right.
Thank you very much.
Bye-bye.
Bye-bye.
All right.
Bye-bye.